Dave here from Vision Optronics. This video demonstrates how we can economically conduct advanced thermography using an off-the-shelf handheld thermometric imager with the application of computer vision, image processing, and visualization tools. These methods were devised as an economical means to perform thermography for our clients and also our internal use. We initially devised this for a customer's type high-power laser test apparatus. In the case of this low-cost imager, the Topdon TC005, we can perform thermography up to temperatures of 550 degrees C with a sampling rate of 25 frames per second and an object resolution as fine as about 800 microns. We're unable to show our customers the apparatus, so we decided to create this video using an induction cooktop and a cast iron skillet. Although it's not comprehensive, please have a look at our website. There you can see some of the types of work we've done. We're experts in vision and motion with years of experience in advanced technologies, especially in the infrared bands. Browse our example programs tab to see some of our past cutting-edge work in industrial and commercial systems, capital equipment for semiconductors and industrial metrology, and instruments for science and space. In the recent past, our main focus has been in machine and computer vision. So check out the recent machine vision tab too. Now, on with the video.
We've been doing some thermography with the Topdon TC005 thermometric imager. I'll introduce the imager here before I get into the details of how we're using it with some computer vision algorithms. This is for a customer program. It's really a pretty nice imager, especially at the price point. Here you can see the aperture for the 256 by 192 pixel thermal imager, and here's the aperture for the 2 megapixel visible imager. At the top are a pair of LEDs which are useful in dimly lit situations. We like having both of these imagers because it can make it easier to set up or to find things rather than trying to find it with only the thermal imager. These two imagers can be fused into one image or used independently. As mentioned, this is a thermometric imager, and that means that each pixel in the thermal array is assigned a temperature that's updated with every frame. The frame rate for this imager is 25 frames per second, which is reasonably fast for a thermal imager of this type. This allows us to measure fairly fast thermal transient events, which is pretty useful for us. In the view mode, you can choose how to display the outputs of the thermal and visible imagers. For what we'll show you today, we only used infrared, but you can choose to fuse it with visible, to do picture-in-picture, choose iMix, which adds an edge calculation to the display and makes it easier to find and display certain things. You can display only the visible imager. And lastly, there's an alignment setting because the imager apertures are not co-located. This causes a disparity between what each measures, and this varies with the range to the object. The alignment setting allows you to minimize this disparity by setting the range to what you're measuring. There's also a color palette. We only used white hot because we're going to run some computer vision algorithms on the saved output data. But while you're using the instrument, these can really help to better visualize what you're looking for. But understand, any image frame data saved to disk incorporates all of these settings into the 24-bit per pixel output files. So fewer features during these file saves means less stuff in the output file. This is often beneficial when we're going to run our computer vision algorithms. The thermometric camera also connects via USB to a PC, so the data stream and files can be analyzed using Topdon's TD-View software. It has a nice set of features, especially for still images, but for this project we needed more than it could do. However, when we pulled the video data down from either the USB or the SD card, it loses its thermometric information, so we had to find a way to reconstruct that. Once we combine that result with the TC005 and our computer vision algorithms, we have an even more powerful tool for visualization, analysis, and design.
Three main tasks were performed with the image data saved by the Topdon TC005: optical character recognition, or OCR, temperature data reconstruction, and data visualization. More in-depth thermography can be performed after these tasks are completed, but we don't cover that aspect here. We perform OCR to find the maximum and minimum temperatures Tmax and Tmin for each frame. These are used in the next task, temperature data reconstruction. Although we believe it might be possible to find the maximum and minimum temperatures from each frame in the video move headers, we decided to apply our OCR methods because we didn't receive an answer from TopDown on this issue. We don't know exactly how the TC005 works, but we've designed, reverse engineered, and integrated similar camera systems. Based on a plausible image processing pipeline, we can describe the reasons for our method. After each higher resolution, greater than 8-bit per pixel, thermal image frame is acquired and filtered, it must be scaled to 8 bits for output to the display. In parallel, the thermometric or radiometric calibration is applied and used to annotate the image frames. No numerical values for Tmax and Tmin for each of these frames are available for temperature reconstruction. So we applied our OCR methods to recover these. The downward arrows represent an image processing progression from the original image in preparation for the OCR algorithm. The raw OCR output is shown in the small block. A 99.63% accuracy was achieved before our parser, extractor, and error corrector. Using Tmax and Tmin determined for each frame is processed into a grayscale 8-bit frame, which is scaled between the Tmax and Tmin limits. To do this, we assume the temperature is linear with respect to the 8-bit grayscale data. The result is a stack of images, with each pixel in each frame represented by a temperature. Now we're ready to visualize the data. 3 methods were chosen to display the temperature fields measured by the TC005 and recovered in our image stack. Color as temperature, height as temperature, and temperature contours. For these displays, some important times to keep in mind are for the peak temperature, which occurs at about 2.6 minutes, and the time that the thermal system enters the temperature control band, which occurs at about 6.2 minutes. It can also be seen that heat energy is applied annularly in the shape of a ring. Color as temperature means that each pixel in each frame is assigned a color from a gradated color scale based on the measured temperature. In this case, we chose to represent increasing temperature with a scale that varies from blue to red. Note that it's rescaled for each image in the stack. Colorization has advantages over shades of gray, also called grayscale. Note the bright yellow arc at the lower left. This is caused by a reduced emissivity, which is much less than 0.95 assumed during TC005 setup. It's caused by a lack of carbon coating. This can be corrected with our software. Height as temperature is a method that allows 3-dimensional representation of the temperature field. Sometimes this makes it easier to see how the temperature is changing over time. To enhance this visualization, we colorized it. In this case, it's clear when the thermal system hits its peak temperature and when it enters the control band. We can also see the action of the thermal control by the height pulsations. Rotating the 3-dimensional body also helps us to see the variations and imperfections in the temperature field. For example, the ring where heat is applied isn't uniform. Also, note the indented low emissivity region. Temperature contours are useful for understanding the direction of heat flow in a thermal system because heat flows from higher to lower temperatures. Temperature is a type of potential that drives heat flux. During the initial heating phase, the higher temperature contours appear to flow radially in both directions from the ring of heat applied, while higher temperature rings are formed over the heat source. When the controller reduces the heat, the contours show a flow of heat in the opposite radial directions as the lower temperature rings appear to converge towards the center and outer edges. During the period in the control band, we can see these rings appearing to oscillate back and forth. Contours around the low emissivity region are also visible in the upper left. To reduce dimensionality, we can use regions of interest referred to as ROIs. This reduces the display from 2 spatial dimensions to 1, which allows time to be displayed as a dimension rather than waiting for time to elapse. We set up some regions of interest to understand the temperature profiles of specific regions of the body. In the upper left, 2 ROIs were created along each side of the handle. This allows us to show how the temperature along the handle is distributed at each point in time. Across the center of the body, a diameter ROI was created. This allows us to understand the radial temperature profile across the body at each point in time. Lastly, because we could tell that the ring of heat wasn't uniform, we decided to make a set of annular or ring-shaped ROIs to calculate the average temperatures of these annuli or rings at different radial distances. We made these annuli have constant area and associated their average temperatures with a geometric center rather than the arithmetic center of each ring. These are shown scanning the body. Next, we plotted the results as colorized surface plots. In these plots, the time response of any of the points on any of the 4 ROIs can be seen. It looks like an underdamped time response, with the controller heating up to a peak at about 2.6 minutes, then cooling into the control band by about 6.2 minutes, where it oscillates around the set point temperature of 104 degrees Celsius. The temperature profile along any of the ROIs for any measured point in time can also be seen in these plots. Note that the diameter thermal profile is similar to a pair of the annuli thermal profiles joined together with one of them mirrored about the center. The diameter thermal profile shows 2 humps which represent the ring of heat applied by the controller. Similarly, the annuli thermal profile displays this hump, but it's much smoother due to the effect of averaging over the annuli or rings for which the average temperatures were computed. In the case of the handle ROIs, we can see that the heat builds up near the base of the handle before soaking towards the tip. Due to a small cross-sectional area, the thermal conductance of the handle is low. However, by the time the control brings the body to the set point temperature, the temperature distribution in the handle becomes more uniform. Lastly, for comparison, we show one side of the diameter thermal profile next to the annuli thermal profile versus time. Comparison shows the variations due to real-world effects or imperfections that were averaged out. If we wanted, we could use a set of diameter profiles to calculate statistical variations about the mean, among other useful analyses. We'll reserve that for another time. We hope you've enjoyed this video. The methods presented are useful for thermography at temperatures up to 550 degrees C with frame rates of 25 frames per second and minimum spatial resolutions of about 800 microns. Using our computer vision and image processing methods, we recovered the temperature data from the top-down TC005 using OCR to create a stack of images that represents a time-varying 2D temperature field. From there, using data visualization methods, we displayed the data, setting us up to do some fairly advanced thermography at a very modest price. These simple tools have been useful for our customers and for our internal use. We hope this will be of use for more of our customers and clients. Big thanks also to MATLAB and Python. Connect if we can be of service. Please leave or send us any comments. Thanks for watching.